Hello everyone, at this video we talk about bits, bytes, nibbles, quick methods to change number bases, and binary arithmetic, addition, subtraction, and multiplication. Let's see the video. Bit, byte, and nibble. In binary, a 0 or a 1 is called a bit. So, one bit is one binary digit, which may be 0 or 1. A bit, if has the lowest weight, is called LSB, and if has the highest weight is called MSB. This is LSB and this is MSB. LSB stands for least significant bit and MSB stands for most significant bit. A pack of 8 bits pertaining to one specific number is called a byte. So here these 8 bits are actually 1 byte. A pack of 4 bits related to each other are called a nibble. In 1 byte we have 2 nibbles, a high nibble and a low nibble. Abbreviations and relations. Bit is abbreviated as lowercase b. For example, internet speed is given in kilobits per second or megabits per second and so on. Byte is abbreviated as uppercase b. For example, file size is given in kilobyte or megabyte. 1 byte is equal to 8 bits. So for example, a download rate of 800 kilobits per second is actually equal to 100 kilobytes per second. Kilobit per second is sometimes written as kb/s, or megabits per second may be written as mb/s. In binary, weights are distributed as powers of 2. So in every place, if we have a 1, it will add an 2 by jth power to the total value, and if there is a 0, no value is added. Powers of 2 that we use mostly are these ones: 2 by 0th, 2 by 1st, 2 by 2nd, 2 by 3rd, and so on until 2 by 11th. 2 by 0th means 1. 2 by 1st means 2. 2 by 2nd means 4. 2 by 3rd is 8. 2 by 4th power is 16th. 2 by 5th power is 32. 2 by 6th power is 64. And 2 by 7th power is 128. You know, these 8 bits here, they are called 1 byte, and 1 byte can range from 0 to 255. We'd better memorize these bits. You know, these numbers, we're going to need them in quick base conversion. 1, 2, 4, 8, 16, 32, 64, and 128. Other powers are 256, which is for 2 by 8th power. 2 by 9th power is 512. 2 by 10th power is 1024. And 2 by 11th power is 2048. You know, these numbers are also needed, but not as likely as the ones that we have in a byte. So it's a good practice if you try to memorize these numbers. In fractional side, we also need to see how things work. For example, here we have 2 by first power, which is 2, 2 by 0th power, which is 1, and then we jump to the fractional part. 1 second, 1/4, 1/8, 1/16, 1/32, 1/64, 1/128, 1/256. These are also needed, and you'd better see them and see how they work. You know, we have 2, 4, 8, 16, 32, 64, and so on. We have them on the fractional side as well. Binary to decimal quick conversion. Let's see how we can quickly convert a number from binary to decimal. Let's say we have a number 101 in binary. Well, the first one has a value of 1. The second 0 adds no value, however, it's standing in the place of 2. And the third one is standing in the place of 4. So if we want to see what this number is in decimal, all we need to do is to add 4, which is this 4, plus 0, which is this 0. Because it's a 0 multiplied by 2, the result is 0. And a 1 that adds a value of 1, and the result is 5. Another example for this, here we have a 0 that's standing at the place of 2 to the 0th power, which is a 1. Another 0 that's standing in the place of 2 to the first power, which is a 2. A 1 that's standing in the place of a 2 to the second power, which is a 4. And another 1 that's standing in the place of 2 to the third power, which is an 8. Among these numbers, 8, 4, 2, and 1, we must add 8 and 4, and both 2 and 1 are going to be 0, because it's a 0 multiplied by 1 or a 0 multiplied by 2. And the result is 12. Another example for this would be 1 byte size. The first one is standing at the place of 1, the second one is 2, third one is 4, fourth one is 8, fifth one 16, sixth one 32, seventh one 64, and eighth one is 128. Among these, we only add 1 plus 2 plus 16 plus 32 and plus 128, and the result would be 179. This is how we quickly convert from binary to decimal. Let's now see how we can convert from decimal to binary in a quick way. Let's say we have a number 151, and we'd better memorize these numbers as I told you at the previous slides. Now, first we think, step 1, is there a 128 in 151? The answer is yes. We have 128 inside 151. So what do? We subtract 128 from 151, the result is 23. And because it's a yes, we add a 0 under 128. This is the first bit. Then we jump to the second bit. Step 2. Is there a 64 in 23? And why 23? Because 151 minus 128 was 23. And we dealt with 128 and we subtracted it. Now we're left with 23. Is there a 64 in 23? The answer is no. We don't have a 64 in 23. So the bit related to 64 must be 0. Then we jump to the next number, which is 32. Step 3. Is there a 32 in 23? The answer is no. Again, we add a 0 under 32 and we jump to the next number, which is 16. Is there a 16 in 23? The answer is yes. So we subtract 16 from 23 and we get to 7. We also add a 1 under 16. Alright? Now we're left with 7. Next, we check 7. Is there an 8 in 7? You know, we dealt with 16 and now we jump to 8. Is there an 8 in 7? The answer is no. So we put a 0 under 8. We jump to the next one, which is a 4. Is there a 4 in 7? The answer is yes. There is a 4 in 7. So we subtract 4 from 7 and we reach 3. And we also add a 1 under 4. Now we're left with 3. It's becoming very easy right now. Is there a 2 in 3? The answer is yes. There is a 2 in 3 and we subtract 2 from 3 and we're left with 1. Because the answer is yes, we actually put a 1 under 2. All we're left is 1. And we also have a 1 here. If this number was 0, we were going to put a 0 under 1. However, this number is 1 and we put a 1 under 1. So 151 is 1001 0111 in binary. Let's see another example for this. Again, we have a 63. We want to convert it quickly to binary. Step 1. Is there a 128 inside 63? The answer is no. Because it's a no, we put a 0 under 128. And we jump to the next one, which is 64. Is there a 64 in 63? Again, the answer is no. So we put a 0 under 64 and we jump to 32. Is there a 32 in 63? The answer is yes. There is a 32 inside 63. So first we subtract 32 from 63 and we get 31 as an answer. And because the answer to step 3 was a yes, we put a 1 under 32. Now we're left with 31, so we're checking 16 and 31. Is there a 16 in 31? The answer is yes. So we subtract 16 from 31 and we get 15. And because the answer is yes, we put another 1 under 16. Now we should deal with 8 and 15, and it's obvious that there is an 8 in 15. So the answer is yes, and we put a 1 under 8 and we get 7, the result of subtraction. Now we jump to step 6. Is there a 4? Is there a 4 in 7? The answer is yes. We subtract 4 from 7 and we get a 3. And also because there was 4 in 7, we put a 1 under 4. Is there a 2 in 3? The answer is yes, of course. We subtract 2 from 3 and we put a 1 under 2. Now all we're left with is 1, and all we're left with here is also a 1. So we put a 1 under this number. A quick method to convert a number from binary to octal. Because we have 2 to the third power equal to 8, we can group binary digits in 3 and convert each pack into octal. Let's see the examples. We have a number in binary 110100. We pack them in 3 digits, starting from the right side. The first pack is 100. 100 has a value of, this is a 0, this is a 0, and this one is a 4. So all we have here is a number 4, which is in octal. The other pack is a 0, 1, 1. This one adds 2 and this one adds a 4. So we have a 6 here. Our binary number is actually a 6-3 in octal. Very easy. Another number 1011. We start from the left side, the first group and the second group. However, you see in second group we don't have 3 digits. It's not needed. However, in order to not make mistakes, we'd better add 2 zeros on the left side of this digit. These zeros actually don't add any value to the number. They don't alter the number. However, it helps us make less mistakes. Now, the first group is 1 and plus 2. So we have a 3 here. The second group is only 1. So we have a 1 here. Our binary number is 13 in octal. And let's see another example, a long one in this case. 1101111. It's actually a byte-sized number and it's in binary. We want to convert it into octal. First, we group them in 3 digits, starting from the right side. First group, second group, and the third group. Like the one that we had here, in order to not make mistakes, we add a 0 to make it a group of 3. Now, the first group is 7. The second group is 5. And the third group is 3. So our number would be 357 in octal. Now let's do it the opposite way. We have a number in octal and we want to convert it into binary, and we want to do it fast. Our number is, for example, 251 in octal. You know, 1 makes 3 binary digits, 0, 0, 1. 5 makes another 3 binary digits, 1, 0, 1. And 2 makes another binary digit, which is 0, 1, 0. So 251 in octal is equal to 10101001 in binary. That easy. Another example, we have a long number in octal. First, we convert 7, which is 111. Then we get to 6, which is 110. Then we get to 0, which is 0, 0, 0. We get to 4, which is 1, 0, 0. And we get to 3, which is 0, 1, 1. So the number is converted, and it's converted fast. So every digit in octal is equal to 3 digits in binary. Now let's try to convert hexadecimal to binary, which is done the same way that we did when we converted octal to binary. Because we have 2 to the 4th power equal to 16, we can group binary digits in 4 and convert each pack into hexadecimal. The process is just like what we did in octal case. Let's see examples. The first example, we have 9 FAD in hexadecimal, and we want to convert it into binary. Here we have packs of 4 digits, because 2 to the 4th power is 16. There is a relation here, so our packs in this case must have 4 digits. The first one, D, makes 1101. The second one, A, is 1010. The third one, F, is 1111. And the last one, 9, is 1001. So 9FAD in hexadecimal is equal to 1001, 1111, 1010, 1101. This is converted very easily, and this is going to work a lot when you want to code or when you are programming or doing things related to that. Number conversion is a very important matter. You're going to need it in IP, Internet Protocol. You're going to need it in computer programming, microcontroller programming, C, C++, Python, and all of them. Now, let's see another example. CB014 in hexadecimal needs to be converted into binary. A 4 in hexadecimal actually means 0100 in binary. A 1 in hexadecimal means 0001 in binary. A 0 is going to make 4 zeros. A B is 1011 and a C is 1100. So as you see here, a number of this length is actually converted very easily and very quickly into binary. So every digit in hexadecimal is equal to 4 digits in binary. Let's do the opposite case, binary to hexadecimal conversion. Let's say we have a binary number and we want to convert it into hexadecimal. Here we make packs of 4 digits and we start from the right side as we did in octal case. First pack, second pack, and third pack. The first pack is an E in hexadecimal. The second pack is a 9 in hexadecimal, and the third pack is a D in hexadecimal. So the number of this length is easily converted into hexadecimal. Let's see another example here. We have 101110 in binary and we need to convert it into hexadecimal. We start packing from the right side, the first pack and the second pack, just like the case we had in octal. Because we don't want to make mistakes, we add 2 zeros at the left side of this number. These zeros don't add or don't alter any value. All they do is that they help us make less mistakes. The first pack is an E and the second pack is 2. So we have 2E in hexadecimal. Now let's see another example. First group, second group, third group, fourth group, and fifth group. Again, we add 2 zeros on the left side to make it a group of 4. Now that the groups are made, we convert each group into hexadecimal. The first group is a 6, the second group is a D, the third group is 0, the fourth group is F, and the fifth group is 3. So the number is 3F0D6 in hexadecimal. Now, quick conversions with fractional parts. For example, we have a number 10.01111 in binary that we want to convert it into octal. In the case of fractional parts, when we want to group numbers, we group them from the left side to the right side. You know, at the integer part, we grouped from the right to the left side. However, at the fractional part, we group from left to the right side. So first we start grouping. The integer group and 2 fractional groups that we have here, we need to add a 0 to make it a group of 3, and we need to add another 0 to the right side. So this 0 that we added here, it actually doesn't change the number. It doesn't add or remove any value However, it helps us do the conversion with no mistake. Now, this pack of 3 digits is related to 2 in octal. This one is a 3 and this one is a 6. So numbers with fractional parts need to be regrouped from left to right, and if we don't have a group of 3 digits, we add zeros to make it a group of 3 digits. Let's see another example. We have this number and this time we want to convert it into hexadecimal. Again, we start grouping, and this time groups must have 4 digits. The first group, starting from left to the right because we are at the fractional part. The second group, again starting from left to right, and we see that we only have 1 digit here. In order to not make any mistakes, we add 3 zeros. And then we go to the grouping of the integer part, which is done from right to left. And again, in order to not make any mistakes, we add 2 zeros at the integer part. Now we do the conversion. The integer part is 2 point. The fractional part is 7, 8 in hexadecimal. Now let's do it in opposite direction. Let's convert 2, 5, 6 in octal into binary. 2.56. Our number in binary would be 010.101.110. But how we get it? 2 is 010, 5 is 101, and 6 is 110. Now let's see another example, this time with hexadecimal. B.E9 in hexadecimal needs to be converted into binary. Our number in binary would be 1011.1110.1001. B makes 1011, and then there is the point, and then we have E, which is 1110, and we have a 9, which is 1001. Now let's use binary as a medium base. What do we mean by medium base? When it's needed to convert between octal and hexadecimal or vice versa, we use medium bases. It means we first convert, for example, from octal to decimal, which is considered as a medium base, then convert from decimal to hexadecimal. However, decimal as a medium base requires more time consumption. So we use binary as medium base, and it's done more quickly. Let's see some examples. Let's say we have a number 346 in octal that we need to convert it into hexadecimal. We want to use binary as a medium base. So we first convert 346 into binary with the methods that we just learned in previous slides. 6 makes 110, 4 makes 100, and 3 makes 011. Now this is our medium base. Now we group our binary number with 4 digits, and we convert each 4 digits into hexadecimal. The result is E6, and how we did it? Well, a group of 4, 0, 1, 1, 0, that makes a 6, and another group of 4, 1, 1, 1, 0, which makes an E. And the 0 is not needed here. So 3 for 6 in octal is actually equal to E6 in hexadecimal. Now let's talk about binary arithmetic, and in this case addition. 1 plus 1 is 2 in decimal. However, in binary, 2 is 1, 0. So in binary arithmetic, we have 1 plus 1 equal to 1, 0. 1 plus 1 plus 1 is 3. It's 3 in decimal. However, in binary, 3 is 1, 1. So in binary arithmetic, we have 1 plus 1 plus 1 equal to 1, 1, which looks like an 11. However, it's not an 11. It's 1, 1 in binary. We want to do some addition in binary. Let's jump to the handwriting part and see how we add it. We need to add 1, 1, 0, 1 with 1, 0, 0, 1. 1 plus 1 is 1, 0. We write 0 here and 1 goes up there as a carry bit. Adding 1 with 2 zeros, we get a 1. 1 plus 0 is 1, and 1 plus 1 is 1, 0. This one is overflow. And this one is carry. Let's see if the addition was actually right. This number is 13 plus. This one is 9. The answer must be 22. Let's see if the answer is really 22. This bit had the value of 1, however, because it's 0, we don't count it. This one has the value of 2. This one adds the value of 4. This one is 0, and the MSB adds the value of 16. Adding these numbers, 16 plus 4 plus 2, we get to 22, which shows that our addition is correct. Alright, as we saw at the other side of the video, the result was 10110. Let's do another example. 1111 is going to be added by 1111. Let's see the other side of the video and come back. We want to add 1, 1, 1, 1 plus 1, 1, 1, 1. Adding 1 plus 1, we get a 0 and a 1 as a carry bit. Now, adding 3 ones results in 1, 1. We write 1 here, and the other one is the carry to the next stage. Again, adding 3 ones, we get a 1, 1. And this is carry, and the result will be 1, 1. So our addition has 3 carries and 1 overflow. Let's see if we did it right. This is 15 and this is 15. Adding them, we must get 30. Values, this one adds 2, this one adds 4, this one adds 8, and this one adds 16. 16 plus 4 is 20 and 8 plus 2 is 10. Adding them, we get to 30 and the result is correct. Alright, the result was 11110. Now let's see another example. We need to add 1, 0, 0, 1 plus 1, 0, 1, 1. 1 plus 1 is 1, 0. There is a carry bit. 1 plus 0 plus 1 again is 1, 0. We write 0 and there is another carry bit. 1 plus 0 plus 0 is 1 with no carries. And 1 plus 1 is 1, 0. So our number was 9 plus 11. 9 plus 11 is 20. Let's see if we have a 20 here. Seems like we do. This one is an 8. No, it's a 4. And this one is a 16. Adding them, we have 20. And the addition was correct. Now we're back and the result was 10100. Let's see another example. The other addition is 1, 0, 0, 0 plus 1, 1, 1, 0. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 1 is 1 with no carries, and 1 plus 1 is 1, 0. We only have an overflow bit here. Let's see if the addition is correct. This one is an 8 plus. This one is 14. Addition is 22. And this bit adds a 2. This bit adds a 4. And this one adds a 16. 16 plus 4 plus 2 is 22. So our addition is correct. So the result was 10110. Now, binary arithmetic, subtraction. In subtraction, we often need to borrow a unit from the upper side. When we are doing subtraction in decimal, the borrowed number will be 1 multiplied by 10, and it will add a 10 to the number in lower side. However, when we do subtraction in binary, the borrowed value will be 1 multiplied by 2, and it will add a 2, which is equal to 110 in binary, to the number at the lower side. The proof for that comes from the Radix formula. Remember the Radix formula? According to the Radix formula, the value difference between a lower hand number and the upper hand number is For example, an on an minus 1 multiplied by r. So r plays an important role here. R is the base of our number. Because we borrow only one unit from the upper side, the borrowed one will be multiplied by r and will show up at the lower side. So in any base if we are, the borrowed number will be 1 multiplied by r. Remember when we were in decimal, the borrowed number was 10, and when we were in binary, the borrowed number was 2, which had been shown as 10 in binary. Other notes for subtraction is 10 minus 1 is 1, and a bigger value cannot be subtracted from a smaller value unless we change the subtraction order and add a negative sign to the answer. For example, we need to subtract 1001 from 1101. Let's see how it works. There is a subtraction 1101 minus 1001. 1 minus 1 is 0. 0 minus 0 is 0. 1 minus 0 is 1. And 1 minus 1 is 0. The result is a positive 4. Let's see if we're correct. This number is 8 plus 4 plus 1. This is a 13 minus. This one is a 9. 13 minus 9 is 4, and it's a positive 4. So our subtraction is correct. This is a positive 4. As we saw, the answer was plus 0100. It's actually a 4. Let's see another example. 1100 minus 1101. You know, the number at the bottom is bigger than the number at the top. So we need to change the subtraction order. Now we can do the subtraction and see what the answer is. We need to subtract 1, 1, 0, 0. 1, 1, 0, 1. The top side is 12. The bottom side is 13. We can't subtract 13 from 12 unless we change the subtraction order. So we change the order. 1, 1, 0, 1 minus 1, 1, 0, 0. 1 minus 0 is 1. This one is 0. This one is 0, and this one is 0. Because we changed the subtraction order, our number is a negative number. So the result is negative 1. As we saw, the answer was 1. However, because we changed the subtraction order, the answer is a negative 1. Another example, 1101 minus 1011. The number at the top side is bigger than the number at the bottom side, so the subtraction can be done without needing to change its order, and the answer will be positive. We need to subtract 1, 1, 0, 1 and 1, 0, 1, 1. 1 minus 1 is 0. 0 minus 1, well, we can't do it here. We need to borrow. So, we borrow 1 unit from the upper side. This one is 0 now, and this one is 1, 0. 1, 0, which is 2, minus 1 will get a 1. 0 minus 0 is 0, and 1 minus 1 is 0. So our answer is a positive 1, 0, which is a positive 2. Let's see if we were correct. The top side is 1101, it's a 13, minus the bottom side is 8 plus 2 plus 1. The bottom side is 11. And the result is positive 2, which is correct. So our subtraction was actually correct. As we saw, the answer is plus 1, 0, which is a plus 2. Another example, 1000 minus 1110. At this case, the number at the bottom side is bigger than the number at the top side, so we need to change the subtraction order. Now that the order is changed, we can do the subtraction. However, the answer is going to be negative. We need to subtract 1, 0, 0, 0 minus 1, 1, 1, 0. In this case, the top side is lower than the bottom side, so we need to change the subtraction order. It's going to be 1, 1, 1, 0 minus 1, 0, 0, 0. Subtracting, we get a 0, a 1, a 1, and a 0. And because we changed the subtraction order, this is a negative number. Let's see if we were correct. Top side is 14. Bottom side is 8. Subtracting 8 from 14, we get a 6. However, because we changed the order, this is a negative 6. And as you see, this one is the value of 2, this one is the value of 4. Adding them makes 6. However, it's a negative 6. So our subtraction was actually correct. As we saw, the answer was 110. However, it was negative. It's a negative 6. Binary arithmetic multiplication. There are some notes. 1 multiplied by 1 is equal to 1, and 1 multiplied by 0 is equal to 0. Now, we want to multiply 101 by 100. Let's see how it works. There is a multiplication here. 1, 0, 1. Multiplied by 1, 0, 0. Just like the decimal case, we start with this one, which is LSB, and multiply this 0 to all of the 3 digits that we have at the top side. So 0 multiplied by 1 is 0, 0 by 0, and 0 by 1. You see we have 3 zeros here. Then we jump to the next one. However, first we should write a 0 to keep the place. Now this 0 multiplied by any of these digits will get us 3 zeros. Then we jump to the MSB. We put 2 zeros to keep the place, and then multiplying 1 by 101, we actually get a 101. Adding the result is 1, 0, 1, 0, 0. Let's see if we were correct. This one is a 5 multiplied by this one, it's a 4. 5 multiplied by 4 will be 20. Now, do we have 20 here? 1, 2, 4, 8, 16. 16 plus 4 is 20, so our multiplication is correct. Let's see another example. Next, we multiply 1, 1, 0, 1 by 1, 1. 1 multiplied by 1 will give a 1. 1 by 0, 0, 1, and a 1. Next, we jump to this bit. However, we need to keep the place. We write a 0 here, and then multiplying this 1 by any of the bits, we will get 11010. Adding them up, 1, 1, 1. This is a 0 with a carry bit, and 1 plus 1 is 0, 1. Let's see if we were correct. The top side is 13 multiplied, the bottom side is 3. The result must be 39. This one is 1, 2, 4. This was supposed to be 8, 16, and we have a 32 here. Adding them, 32 plus 4 is 36, and 38, and 39. So our multiplication is correct.